During the course of this presentation, we'll cover periodic engine and chassis maintenance, engine removal, engine overhaul and component reconditioning, and engine assembly. We'll also cover carburetor service, electrical systems operation and troubleshooting, and we'll finish up with fork rebuilding. The Venture's electrical components are quite similar to those used on various other Yamaha models. Electrical systems, whether ignition, charging, or lighting, all operate on the basic theories of electricity. If you understand how a system works, chances are you'll be able to troubleshoot it easily. During this portion of our program, we're going to review the basic operation of the ignition system, charging system, and the electrical portion of the cooling system. We're also going to show you how to effectively troubleshoot these circuits. The transistor-controlled ignition system used on the Venture is fully solid state, having no moving or mechanical parts, and it relies on the motorcycle's battery as a power source. This diagram shows what would be a single-cylinder TCI system. The main components are the battery, main switch, primary and secondary ignition coil windings, the control unit, and the pulsar coil. When the ignition switch is turned on, operating current is supplied directly to the control unit. It also flows through the primary side of the ignition coil, through the control unit, to ground. As current flows through the primary winding, an electromagnetic field is produced. As the lines of magnetic force, or flux lines, cut through the secondary winding, a spark is produced. Since the expansion rate of the field is limited by battery voltage, in this case 12 volts, the speed at which the flux lines cut through the secondary and the field expands is relatively slow. The spark produced is quite weak, and we refer to it as the wasted spark. It occurs as the piston approaches top dead center on its exhaust stroke. When the rotor projection passes over the pulsar coil, a signal is transmitted to the control unit that then interrupts the flow of primary current to ground. Since the primary circuit is no longer grounded, current can no longer flow through the primary coil. The current flow stops, and the magnetic field around the primary collapses very quickly, causing a much stronger spark than occurred during the buildup of the field. The reason we get a much stronger ignition spark here is quite simple. When we switch the current to the primary coil on, it takes some time to saturate the coil and build a magnetic field. Remember, we're working with only 12 to 14 volts here. The expansion of the field is relatively slow, and therefore the speed at which the lines of flux cut through the secondary windings is also relatively slow. The spark produced is fairly weak, but once this magnetic field is established and we then cut the flow of current, it collapses instantly. This sudden collapse induces very high voltage in the secondary and a good strong ignition spark. From here, the rotor continues to turn until again the projection passes over the pulsar coil. This time, the signal produced causes the control unit to again allow primary current to flow to ground. The current flows through the primary winding, and the field builds. Now, how about troubleshooting? Well, the first things to consider when troubleshooting any ignition system is firstly, how does this system operate? And secondly, where are the weakest points? We've seen how this system functions, and we know it relies on battery voltage. If the battery were unable to provide adequate power, would this system operate properly? Quite frankly, no. Any ignition system that relies on battery current not only requires a good battery, but also a charging system that's working properly. So before you dig into the ignition system itself, check the obvious. Make sure there's enough current available. Check the battery and the charging system. At the other end of the system, we have the spark plug cap and the plug itself. If the plugs are badly worn or excessively gapped, they can overtax the system to a point where misfire will occur. Perform a visual check and replace them if necessary. Also, check resistance through the plug caps. The spec here is 10,000 ohms plus or minus 10%. Keep in mind that this system was designed to use resistor-type caps. The use of non-resistor types will affect overall operation. Assuming the charging system, battery, plug caps, and spark plugs are all in good condition, and also assuming that you've made sure the various wire harness connections are secure, the next step will involve performing resistance checks on the remaining components. Pulsar coil resistance is checked by connecting an ohm meter between the pulsar lead and the common ground lead. Specified resistance is 110 ohms plus or minus 15%. To check primary coil resistance, connect your ohm meter to the red-white wire leading into the ignition coil and to the wire leading from the coil to the ignition control unit. Specification here is 2.7 ohms plus or minus 10%. In order to check secondary coil resistance, the spark plug cap must be removed. The ohm meter leads are connected directly to the high tension lead and again to the wire leading to the control unit. Your ohm meter should read 13.2 on the ohms times 100 scale, or 1,320 ohms. Specification here can vary plus or minus 20%. Resistance through any electrical component should be measured twice, first when the component is cold, and again when it's reached its normal operating temperature. Now, let's have a look at the 4-cylinder version of this TCI system. The Venture ignition system is really just 4 of these individual systems combined. If we add 3 more pulsar coils, each with its own color code and an additional rotor projection, now each projection triggers 2 individual pulsars. Add 3 more ignition coils, and we have a complete Venture ignition system. We now have, with the exception of the control unit and power source, an individual ignition system for each cylinder. Number 1, 2, 3, and 4. We haven't yet talked about checking the control unit, and we'll get back to that in a minute. It's the last item that should be considered. Tied to this ignition system are a number of safety interlock circuits. The side stand switch will shut the ignition system off if the stand is left down and the transmission put into gear. There's an emergency stop switch located under the dash panel that will also shut the system off if the bike is leaned past 60 degrees. Your shop manual outlines the procedures for checking these components, so take the time to read up on them. Anything that's tied to this system can affect its operation. Loose connections, worn switches, even moisture, if it's trapped in the right place, can cause problems. So before you start replacing parts, check every possible item in the system. Now for the control unit. It cannot be checked accurately with a simple ohm meter. If all the other components are in good condition, you'll have to assume that it's at fault. Plug in a new one and try it.